so please submit any questions you have and we'll do our best to answer them. Hello and welcome to today's webinar, Harnessing Reliability Analysis for Optimal Results. My name is Sean Shapiro and I'm an Area Marketing Manager here at Minitab. A few housekeeping notes before we begin. We'll have a Q&A session after this presentation, so please submit any questions you have and we'll do our best to answer them. We recommend viewing this webinar via laptop or PC for best results. If you experience a delay or sync issues with the audio and slides, please exit the webinar and rejoin or refresh the page. We will send a copy of the recording following this webinar, so there's no problem if you miss anything or you'd like to review afterwards. I'd like to introduce our presenter today, Cheryl Pammer. Cheryl is a Senior Advisory Statistician in Minitab R&D. Cheryl has worked on the project teams that help develop many of Minitab's most popular features, including Assistant, Design of Experiment, Gauge R&R, Reliability Analysis, and Predictive Modeling. Drawing on more than 25 years of experience in teaching, statistical consulting, and software development, Cheryl aims to provide the sound statistical strategies and software tools that professionals need to solve the real-world problems they face on the job. We're so excited to have Cheryl here with us today, and with that, I'll hand it over to her to begin today's presentation.
Thanks, Sean. So today we're going to just do a little overview of reliability to get everybody kind of on the same page. We'll talk about some reliability terms and techniques such as censoring and how probability plots work, as well as look at parametric and non-parametric reliability techniques, the hazard function, and finally, one of Minitab's latest additions to the reliability area, Cox regression. So let's get started. When we talk about reliability, one thing just to understand what we're talking about, it's simply a probability. Reliability is the chance or the probability that a system or product will perform its intended function under normal operating conditions for a specified amount of time. So the benefits of reliability will be things like predicting your product reliability, looking at even comparing two products to each other in terms of their reliability and how long they'll last, looking at warranty costs, and assessing the effect of possibly changing the design of a product. But reliability gets some special techniques that are important to some of the problems that come up in this area. So, for example, most of the time when we're looking at statistical techniques, we're focused on the mean or the 50th percentile. We're often talking about a normal distribution. We might have reasonable sample sizes and we see all of our data. Well, reliability is different because, first of all, we're very rarely looking at the 50th percentile. You can see the picture on the right here. We're looking at a suspension bridge. Nobody cares when 50% of those cables fail. We're much more interested in the tails of the distribution. So we're going to look at when 5% of our product might fail, or what percent might fail in the early warranty period. So because of that, because we're not concerned as much about the center of the distribution, we're estimating the tail ends. We often have to look at non-normal distributions. We don't have bell-shaped curves because, first of all, if you're looking at a failure time, it's going to be cut off at 0. And now we have to actually look at the right side of that distribution. In addition to that, we often deal with really small samples. So if we're talking about things like looking at the space shuttle data, right? We've only had a handful of them. So when we look at the reliability analysis on certain parts, especially in areas like aerospace, we're often talking about very small samples. Or if, let's say, we're in manufacturing and we get to build prototypes, we only have a handful of prototypes. So we don't get some of the luxuries that come with much larger samples. The other thing is, in order to get really reliable products to fail, we often have to accelerate the failures by doing things like getting a microchip to fail by adding heat and humidity to it. So we have to accelerate and sometimes extrapolate back to normal use conditions. And finally, we often have to deal with censoring. And we'll talk next about what we're talking about with censoring. So when we have censoring, we have information about when something might fail, but we don't know exactly when it will fail. We just know that it's lasted a certain amount of time. So if you look at this screen, you'll see we have a timeline at the bottom. We have kind of a start time and an end time. And there are different kinds of censoring we might see. At the top, if we have something failing between the start and the end time, there we have no censoring at all because we know when the failure time was, right? And we know when the start time was, we know when things failed. If we have to end our study, or we're looking at something like maybe warranty data where I've seen a handful of failures, but I also have the thousands of parts out in the field that haven't failed yet, that's right censoring. So on the timeline, it means that the censoring time is somewhere out to the right. We know it's lasted up till today, this time point when we're doing the analysis, but it hasn't failed yet. So that failure time is out on the right on the timeline. Right censoring can happen before we end a study too. It just means that, for example, in healthcare, we might have had a patient leave our study before the end of the study. So that's also right censoring because we don't know what happened. We know they lasted this long, but we don't know when the failure actually occurred. Or maybe a failure occurs for a different reason. So we know we had a failure at 20 hours, but it didn't fail for the reason we're looking at. So it is right censored for that reason. Left censoring does not occur as much in reliability in the manufacturing area. It occurs more in healthcare. Left censoring means that on the timeline, the actual start time is missing. We have a failure time, but we don't have a start time. The most common case for left censoring would be we have when someone died from a disease, but we don't know when the onset of the disease was. And then finally, interval censoring. Interval censoring just means we have a start time, we have an end time. We don't know when the failure occurred. It happens somewhere in that interval. The most common case of interval censoring is going to be warranty data, because a lot of failures, if you think about your car, for example, the failure will be reported back to the manufacturer within a mileage interval, 10 to 20,000 miles, for example. So we don't know exactly when the failure occurred. The other case where we might see interval censoring is if we just have actions, say, once a day. So, for example, if we're doing a study with, let's say, in the medical field with rats, we might just inspect what's going on with the rats once a day. We don't just keep watching them all the time to see when one of them keels over. So we have a start time and end time, and we know the failure occurred between, say, 12 hours and 24 hours. We just don't know exactly when. So using all that, and what I think is really amazing about reliability is how all this stuff is important to the analysis. And I want to talk briefly about how we can incorporate censoring into our analysis and how it often is very helpful to see, because if we don't think about the units out in the field or the subjects that have not failed yet, we are not getting a full picture of what's going on with our data. So let's do this brief example. I've got 5 failure times on my screen. So things failed at 1.5 hours, 3.1 hours, etc. Using those 5 observations, we can add them up. They add up to 15, divide by 5 because there's 5 of them, and we get a mean time to failure of, say, 3 hours. Now, if we have censoring, how does that affect our mean? Well, let's say we have an observation that didn't fail at 6 hours. So we'll add that observation. We'll say it's the 6+ observation, right? So we know it lasted 6 hours. We stopped our study. And if we kept the study going, it failed somewhere beyond 6 hours. So we could take the mean of the data, right? And that's just adding up those data points. We get to 21. Now we have 6 observations. So 21 divided by 6 gives us 3.5, and we could say our mean time to failure was 3.5, but we're not really doing justice to this data because that last observation didn't actually fail. So we want to give a little credit for the plus. And there are many ways you can do this statistically, but in general, they all use the same concept, and that is we're going to look at the number of failed and how the total time adds up. So we have a total time of life of 21, and that includes the 6, right? 1.5 plus 3.1 plus 5.7, etc. So we can add up the total time that things have lived and divide by the number of 5, and now our mean time to failure has given credit to the one that hasn't failed yet by giving us a mean time to failure of 4.2. And as expected, that's higher than just taking the mean of the data, right? So that's the goal with censoring. When we incorporate censoring in our analysis, we're going to actually give credit to things that haven't failed yet, as we should. Now, one more concept that comes up really heavily in reliability, and I mentioned that earlier, we're often not actually interested in means, right? We want to know when things start to fail. We have a product out in the field that we're just starting to see, say, warranty claims come in. So maybe we only are seeing 1% of our product has failed. How do we incorporate other distributions, other percentiles, and censoring into an analysis? And it turns out one of the most popular tools is a tool that you may have used for other reasons. A lot of us use probability plots to assess whether, say, a normal distribution is a good model for our data. But it turns out probability plots have kind of a magical place in reliability. Let's see how. So if we look at the same data again, all I've done is I've ordered it. I put it in numeric order. The earliest failure happened at 0.5 hours or days or whatever. The next failure was 1.5, and then we have our censored observation out there at 6. If I order the data, then they have a ranking, right? Number 1, number 2, number 3, number 4, number 5. And then after that, I don't know what the ranking is because those are the censored observations that I don't have failures for. And right now I only have 1 censored observation. Without assuming any distribution at all, though, I can estimate what percentile that observation is. Now, one way to do it is just take the ranking, the first observation, right? Out of 6 observation is 1 divided by 6. We could just take I divided by N. But it turns out, statisticians need to keep ourselves in business by making things a little more complicated. We have a correction that we put to that. So when we estimate percentiles, there are actually a couple different ways you can do it in Minitab, but the default for probability plots, for example, is taking the rank number I minus 0.3 and then divide by the total number, including those that failed, plus 0.4. And that gives us an estimate of the percentile. So for the first observation, it's 1 minus 0.3 divided by 6 plus 0.4, and if you check my math, you're going to find out that that number is, that percentile is 10.9375. So all I'm saying is at 0.5 hours, we have about, or we can expect about 11% to have failed in our population at about 0.5 hours. If we go down to our last failure, which happened at 5.7 hours, we would estimate its percentile to be 73.4. What that means, or how that's interpreted, is we're saying that, okay, we expect about, in this population, 73% to have failed by 5.7 hours. Now, the problem with doing this is actually a non-parametric approach. We're not using a distribution here on the left at all. But then we can't really get predictions in between, right? So if we want to predict, let's say, the 15th percentile or even the 25th percentile, right? That falls between the first and second data point where we have failures. So to do that, we want to actually add a distribution. And the way that's done is we basically can look at different graph papers, so to speak, and figure out which one has scales that correspond to a straight line on that graph paper for these data points. So the data and the percentiles you see in the table on the left are actually those blue points on a probability plot. And here you can see they're blue points on the graph for a Weibull distribution. The Weibull distribution, if you look at the scales, the Y scale and the X scale, they're not linear, they're not spaced evenly apart. for a Weibull distribution, it turns out that there's kind of a lot of space at the bottom, and then things kind of crunch up more at the top on the y-axis. And then the x-axis, which is the axis for the actual failure time, is a log scale. So that happens to be the graph paper, so to speak, we use for a Weibull distribution. And back in the day, before we had fancy computers and Minitab to do these calculations, they were all done on hand by pads of Weibull graph paper, basically, because we can calculate from the table on the left by hand or with a simple calculator what those blue points are. Those are your percentiles. And then even without a computer, we can draw a good line, our best line through those points. And now we can estimate any percentile we want. So for example, if you wanted to know when approximately 20% of this product's going to fail, go up the y-axis to 20, read across, hit the line, and go down, and notice that'll be at about 1 hour. So really, really cool, powerful stuff. And notice the other thing is this graph ends at roughly 80% because we have some that haven't failed yet. So that failure or that censored observation of 6 doesn't even show up on the graph. And it doesn't matter. We can have only a handful of failures down on the bottom left corner of the graph. As long as we have 2 of those, we can draw the line further up. And that's what's done a lot in reliability. We often have to do what we don't do in most other statistics. We often have to extrapolate to what might happen in the future and continue drawing that line beyond where we have failures. Okay, so now that we have kind of the most important concepts of reliability, let's put an example behind this and we'll start moving a little more quickly. This could be any part, but this turns out to be an example that I was working with recently. We're looking at a heat exchanger for an HVAC system. So basically think of your heating and air conditioning unit in your house. One of the important pieces of that is this heat exchanger. They also exist in your cars. They're everywhere, believe it or not. But recently, there was a specific case where there was a recall because they had seen a lot of unexpected failures, right? And I won't say the company or necessarily the industry, but that's what we're going to investigate here, these failures in the heat exchanger. And we're going to start by saying, okay, we have all these out in the field. So how do we even know how many we expect to see under warranty? We know there's a problem. We know we're seeing more than we expect to see. What's going on and what do we expect that to cost? So the first thing I want to show you is how warranty data often looks. So basically, in this case, these are yearly data because this is an HVAC system. These are expected to last, these heat exchangers, roughly 20 to 30 years. They were starting to see failures at 3 to 4 years. So I have a start time and I have an end time. And notice in row 1, I didn't have any in the ones out in the field fail in year 1. So all of year 1 is just censored. So that means I have no end time. It's a missing value in Minitab. So I have the start time of 1 year, the end time missing. I actually could have another row, except they stopped putting these out, where it was just 0 to 1 year, anything that's failed within the first year. I just don't have any units that out in the field anymore that I'm putting out now because we stopped production on this particular item. At 2 years, I also didn't see any failures. 2 years star means 389 units have been out in the field for 2 years, and none of them have failed yet. Now, for year 3, in the 3 to 4 year, right, I had at least 410 units out in the field, 409 plus the one that failed, but I had 1 failure. So between 3 and 4 years, I had 1 failure, and then I have those that have been out 3 years. 409 of them are still out in the field and haven't failed yet. So that's how we often see, and the best way to analyze data that's warranty analysis data. Now, I want to step back because a few weeks ago, Minitab released our Minitab reliability module. And the goal with this module, we have these reliability techniques in Minitab. They've been in Minitab for many, many years, but we wanted to make them easier for you to access based on the type of problem you have. So here, the reliability module has, do you have a simple kind of reliability Weibull problem? Do you just want to estimate the distribution, estimate the reliability of a product, etc.? Are you looking at warranty analysis? Are you trying to demonstrate a certain requirement? Are you looking at mean time to failure for a repairable system? Have you done some sort of accelerated test that I mentioned earlier where we add something like heat and humidity and we accelerate failures? Or are you looking at some other life data model? So by looking at the reliability add-on module, we can go quickly to, all right, this is the problem we have. We have warranty analysis here. That's where I want to start. I'm going to choose that. And then within the warranty analysis area, we have different problems you might want to be solving. One of them being what I just talked about. Sometimes we have to convert the data. We have tools in Minitab that help put your data into the framework you just saw to make it easier to analyze your data. We already have our data all ready to go. We already know we're going to use a Weibull distribution, so we're not going to identify the distribution, or we're just going to go straight to the warranty prediction here. So fit a distribution to warranty data. That was my data. I'm going to fill out this form with those start, end, and frequency. I'm going to say the length of the warranty here was 10 years. I'll put that in. And my average cost per failure in these heat exchangers isn't crazy high. It's only $150. But what I want to do is look at how many items, how many of these heat exchangers I expect to see fail in the next few months or next few years. In this case, because my data is in years, this is yearly data. If I wanted to change it to monthly data, I could have. But next year, I know out in the field right now, I have 4,286 units. And you can see in the green box, this is what I'm looking at. Of all those units out in the field, Minitab's taking into account how old they are, et cetera, and it can predict how many failures we expect to see. We expect to see roughly 5 failures in the next year. And that is kind of small for a lot of industries, but in this case, that failure could be life-threatening because of carbon monoxide, et cetera. So we care. We've recalled this product, actually. We want to know of the stuff that's out there, how many failures might we see, and also what the predicted cost is. Now, again, these weren't overly expensive. They were just important failures to address. At $150 per the predicted cost of those roughly 5 failures would be about $735. And this is what we expect to see in the next year. We can also put confidence intervals around it. So, I predict 5 failures, but I can also be 95% confident that I'm going to see somewhere between 1.5 and 11.5 failures. So I could see as many as almost 12 failures in the next year of the 4,286 units that are currently out in the field. If I want to accumulate that further, in the next 5 years, this is the purple box, I predict around 30 failures with a confidence interval of somewhere between 19 and 41 failures. So I could see up to 41 of these fail in the next 5 years. Really, really useful stuff. And again, a lot of times we see more failures than that. This is just a concern because of how dangerous some of these failures could be. All right, so we've done the warranty prediction with the data that's out there. And what's really cool is, again, we don't have a lot of failures, but we're using all of the systems out there to actually get these predictions, right? We're taking all of these units that are out in the field, still running, not having failed to get really accurate predictions of how many might fail. So we've used sensoring to be able to get these really good data points of things that we have kind of no data for, right? But we know how long they've lasted so far. Now we're going to go back and try and improve this problem. We have to redesign this part, right? We know we have this specific mode of failure, and our goal is to redesign the part and compare the existing design, this is what's out in the field, to this new design. Now, I'm going to change my data now to hourly data, not yearly data. And what I want to do is I'm bringing this back to the lab, and I'm going to do some sort of something to accelerate the failures, right? So in this case, I'm probably adding heat and humidity, extreme conditions to try and get these to fail faster, because if I redesign this and these things, tend to last 30 years, I'm not going to see any failures for a few years, right? We know that already. In the data that's out in the field, the first failure we ever saw was in 3 years. I can't wait 3 years to fix this, right? So I'm going to have to accelerate my failures and look at, did my new design under these accelerated failures actually improve the problem and really solve the problem? Does it extend the life for these things? So in this case, I'm accelerating the failures. Sometimes we're going to extrapolate these back to normal conditions. In this case, I'm not going to. That actually only makes a difference in terms of what tool you use to analyze the data. So let's go back to our tools here. If I were accelerating back these lab conditions to real life, so taking my hourly data in the lab under accelerated conditions and extrapolating back to what that means in terms of how many years they're going to last in the field, I would be doing accelerated life testing. In this case, even though I'm accelerating my failures, I'm just going to do the classical, most common tool, just a simple reliability. Sometimes we call it a Weibull analysis, because most of the time with reliability data, the most common distribution is going to be a Weibull distribution. Just like in almost every other thing in statistics, most commonly we use a normal. In reliability, we almost always use a Weibull distribution, and we'll talk about why, but it's also called Weibull analysis. All right, so we're going to go to our reliability/Weibull analysis and analyze our lab data. Now, when I click that I want to do this, I get a few choices. And again, we're using the Minitab newly released reliability module. I could identify an appropriate distribution. If I don't know that I want to use Weibull, I could just go through and look at a whole bunch of distributions and kind of pick the one that fits best. In this case, I'm going to start with the Weibull. If it looks bad on the probability plot, the line doesn't go through the points well, then I might go back and do distribution identification. But we're going to just start with just an overview of what's going on, comparing the new to the old design. So I choose distribution overview. I'm going to fill out the form again. I've got my failure time. One thing we had in the data we had a column, and actually I'm going to go back and show you this data again. We had a column that identified whether an observation was censored or not, meaning we still, even though we accelerated these failures, we still had some things that didn't fail yet, right? So I have failure times, and I have whether they actually failed or whether they lasted this amount of time, and then we stopped running the test because we moved on to the next unit. So I have a mix of things that actually failed and things that did not. So I have a censoring column. So this is typically how you would set up the data like this in Minitab. You have your failure time, your censored observation, and if you're comparing two groups, you have a column representing the groups. So now putting that data into my form, I'm going to put in my failure times. I have to go into the censoring subdialog and put in my censoring column, and I have to tell Minitab which value is censoring. So if you think about it, you could have zeros and ones if you want to. Are the zeros censored observations or the ones censored observations? In this case, the yeses are censored observations. The one thing that I will kind of warn you about in Minitab, when you put in a text column for censoring, and that's what we have. Yes and no has text in it. We do have to put the censoring value in double quotes. So it'll be double quote the word yes with the capital Y, just like it is in my worksheet, and double quote. That's one little thing that's a little bit awkward, but once you know about it, not so bad, right? You have to put the censoring value in double quotes if you're using text values. If you're just using zeros and ones, you don't need the double quotes. Okay, so going back, we've got we call it a by variable because we're just comparing a few groups. So we're going to look at the failure by design, meaning we're going to compare the old design to the new design. And I'm just starting with the Weibull distribution. I almost always do that in reliability data. And then if that doesn't fit well, then I might do a distribution identification. Okay. So here we do get an overview of our data. The blue line is our new design. The red lines here are our old design. And we can see it in a few different ways. That's one thing I do like about the distribution overview flat. In the top left corner, we see the overall kind of shape of the distribution, right? We see that the new design, the blue line, is maybe kind of close to a bell-shaped curve, although it still has a longer right tail. The red line, the old design, definitely has a non-normal distribution, right? It's got a very right skewed long tail on the right. And if you think about it, think about what we care about here is when those failures might happen. That overall distribution with the new design, the blue line, has moved to the right. That's good news for us. We can repicture this in a couple different ways. So we're going to take that concept of the distribution curve and now move it to a probability plot, which we just talked about, right? We're going to put it on that Weibull graph paper. And the Y scale on this represents the percentiles for a Weibull distribution. The X, or the horizontal scale here, represents the failure time on a log scale. And we see the blue line is to the right of the red line. And so we see that the new design did extend the life. It moved to the right. One thing about using the distribution, and I mentioned this before, we could also predict any percentile we wanted to. So we could use that probability plot, go across it, say 5%, and look at when we expect 5% to fail, right? Or we could look at when we expect 10% to fail and read that directly from the graph. We could also look in our results window, and we get tables that show us all those percentiles. But you can also read all those percentiles from the graph. What we see, though, is we're always doing better with the new design. The curve on the bottom, we call the survival function. We can also call it the reliability function. This is looking at how the reliability changes over time. So when you think of the probability plot, it's looking at the percent that fail over time. The survival function, or we often, again, call it the reliability function, is the inverse of that. That's looking at how many survive over time. So we're going to look at the glass half full. And we see at the beginning of time, 100% survive. And then over time, we see the reliability drop. What's really exciting is with the new design, we don't see that really crazy drop right away like we did with the old design. So again, the survival is better with the blue line, much, much better than the red line. So the new design is very promising for us. And then the very last thing on here, the hazard function. We're going to talk a little bit about that because it's important for a couple of reasons. It's really where the Weibull distribution comes from. And we're going to start looking at some reliability modeling that specifically uses the hazard function when we look at Cox proportional hazards models. So the hazard function, you can see, just for reference, the red line's on top of the blue line, and we know the blue line's the better one, but let's look at why. Let's talk about what a hazard is. The hazard rate, or the hazard, is really just the instantaneous rate of failure, the chance that something will fail in a specific instant. So again, if we look at our timeline, we've got a specific time, and then we have just this instant to the next time, right? tiny, tiny little instant in time, what is the chance that it's going to fail? So at any given instant in time, what is the chance something will fail? And the reason why we care about the hazard is, first of all, the Weibull distribution was actually not developed by a statistician. It was developed by a reliability engineer specifically for reliability problems, all based on the concept of a hazard. So this graph on the left, you may have seen before. It's actually out there on the internet. I didn't create it. But if we think of any product, think of your car, think of your air conditioning system, think of your computer, right? Any product has like an entire life. And it turns out that at the beginning of a product's life, there is sometimes a high chance of failure, especially when we look at things that like electronics, right? If something's going to fail early on, it's going to fail right away because most likely there was a manufacturing defect, right? So let's say we're talking about something electronic. Something was welded incorrectly on a circuit board, right? If you think about the concept of light bulbs, if you go to a light bulb factory, they actually turn on all the light bulbs before they're packaged, right? And some of them will fail right away. Often, again, that's a manufacturing defect. That's what our warranties are supposed to catch, right? They're supposed to catch any manufacturing defects. Same thing with a car. A lot of states have lemon laws, meaning if your car fails within a certain number of months of when you purchase a new car, they immediately have to replace that car. That's to catch the left side of that blue curve. We call those infant mortalities. And then we have the useful life of the product, right? In the case of an HVAC system, that might be, roughly 20 to 30 years. That's when any failures that happen are somewhat random. Failures still happen, but the product's not really wearing out. It's just, stuff happens, failures happen. And then when we look at the right side of that blue curve, that's when we actually see failures start to increase. So again, think of your car. Once you get a car that gets to be like 10 years old, you start having to repair it more often, right? You're in the wear out period, maybe even before that with certain cars. So we talk about the entire life of a product being that blue bathtub curve. Well, it turns out no distribution really models all parts of the bathtub curves, but certain distributions, like the normal distribution, for example, will model wear-out failures, only wear-out, because the hazard for a normal curve is always going to be that yellow line. The hazard is always going to be increasing if you choose a normal distribution. If you choose a Weibull distribution, the Weibull distribution has something known as a shape parameter, which actually determines what it looks like. We call it kind of the shape shifter distribution, because if the shape parameter is less than 1, it means you're modeling a decreasing hazard. Or the left side of the bathtub curve, the red curve here, the hazard looks like this. You start with a high failure rate and things slow down. Again, that's your manufacturing defects. The Weibull can also represent the middle of the bathtub curve. If the shape is around 1, that's the useful life of a product. That's the random failures that occur, the green line we see here. And then finally, the Weibull can also model the wear-out failures. So if a Weibull distribution has a shape bigger than 1, it's modeling wear-out. This is important because for a couple reasons. It's why the Weibull is so popular, and it also can help you look at a reality check. Is this type of failure making sense? If we go back and looked at this data a little more closely, you would have seen that the Weibull curve for this data was actually a wear out. The hazard was increasing. Actually, we can go back and see that. The hazard for this data is actually increasing because we're talking about a wear out failure, right? This hazard function, the line goes up. We're on the right side of that bathtub curve if you look at the graph in the right corner. The hazard is increasing. Regardless of whether we're looking at the new design or the old design, it's just that the old design increases faster. So the instantaneous rate of failure is higher for the old design. Now, We can also look at distribution overview just as to contrast in a non-parametric way. We don't even have to assume a distribution. I can go back to the same dialog box and choose in the distribution overview that I want to do the non-parametric analysis. We get similar results. We see we can get a reliability function and we get a hazard function that look very similar to what we had when we used a Weibull distribution. The difference is when we don't use a distribution, we only get estimates where failures actually occur. And so our survival function will no longer be a nice smooth curve. It'll be a step function, right? And we only can estimate the reliability where we actually saw data. Same thing with the hazard. The hazard's a step function that changes steps every time we see a failure. So I'm putting this out there, though, because one of the concepts of this non-parametric hazard is something we're going to use in our next technique, which is one of the coolest reliability modeling techniques actually is what we call semi-parametric. It's not parametric like using a Weibull distribution. It's not non-parametric like using no distribution at all. Semi-parametric uses both together. And that's why we're going to focus on this hazard function here for a minute. So the hazard rate at time t, again, is another way to say it. It's the probability a unit that survives until that time will fail in the very next instant, right? So we could use this. We could look at this using the Weibull distribution. We did that earlier. Here we're looking at the non-parametric hazard, but we see the same thing. We see that the hazard rate is steeper for the old design, meaning that red line, the instantaneous chance of failure is steeper. The hazard, the risk is higher for the old design. The new design has improved the hazard function, meaning it's things are lasting longer, right? It's moved out to the right. The failure times when they happen are happening later. And the instantaneous rate of failure, the hazard, although it's still happening, it's still wearing out, it's happening later. So that's really exciting and key for us. And we could do a hypothesis test around this too. I have done it. And what I found was it is a significant difference. So we do see that the new design is significantly better than the old design, right? If you wanted to do this, going back to that first part of the reliability module where it's just doing the reliability Weibull analysis, we don't have time today, so we won't cover that. But if you wanted to just test to see if those differences were significant, you can do it both using a Weibull distribution under parametric distribution analysis, highlighted in green, or we could use the don't assume a distribution at all, and that's the box in blue. Go in, use the non-parametric distribution analysis. Both of those have tests for differences between groups. So when you put in that group as a bivariable in those two dialog boxes, you can actually test to see if there's a significant difference. But the problem is, in this case, what about other variables that might be going on, right? So these will only look at differences between one factor, so to speak, right? So I could compare using either of these tools, new design versus old design. But what if I need to include some other things? And here I do. There are other things that affect the lifetime of a heat exchanger. So I also want to include things like the vehicle model, or in this case, it's an HVAC system. I want to include the model of the HVAC system. Where is the heat exchanger located within the unit? What's the velocity of the fluid that flows through it? There's a lot of other things that impact this. And so if I want to take those into account, I'm going to use the Cox proportional hazards regression model. And I am really excited about this because I think it's been a long time coming into Minitab. Again, this is actually what we call a semi-parametric model, which I think is kind of cool, meaning it's using the non-parametric hazard you just saw, but putting a regression around it. So if you look at this equation, we're saying there's a baseline hazard rate. In this case, maybe it's the existing design has a certain hazard. And then we can put a model behind this to increase or decrease that baseline hazard rate. So that basically we've got the hazard given certain x's. So the hazard on the left side of the equation, this is saying the hazard at time t given values of x, and x might mean new design, fluid velocity at 100, and product location B, and all these x's, just like in a regular regression, right? But what we're going to do is we're going to look at how does the hazard, that's kind of our baseline, change based on just a model. So this right side, this is going to increase the baseline hazard. The hazard, in this case, the baseline hazard is going to be the old design. How does that old design change based on all of these things that I can change in an actual model? So the model itself looks a little bit like a logistic regression model with an E in it. Minitab actually uses it, simplifies the model, and you'll see that in a little bit. But that's all we're doing. We're taking a baseline hazard and seeing how various predictors change that hazard up or down, right? Various combinations of predictor settings can move that hazard. So it models the relationship between the time to an event and one or more predictors. This is used a lot in biostatistics, actually. I was recently working with a researcher who happened to be my daughter on a problem like this, using Cox proportional hazard to look at patient demographics to choose the right treatment, cancer treatment for a particular type of leukemia based on the patient demographics, right? So we can look at how, okay, the fact that this person is 45 and was diagnosed with this particular thing and has this mutation, et cetera, all of those are predictors that go in this green part of the model. And guess what? From that, we can actually choose the right course of treatment, right? It's just amazing. So it's used a lot in that area. Here we're using it more in a reliability sense, manufacturing, where we're just going to compare the risk of the new design versus the old design. So now I'm in the model part of my reliability module. So I'm in the fit life data model. There are a couple different models we offer, but this one that we're going to focus on, which I think is really, if you don't even know where to start, a great one to look at, it's the Cox model with fixed predictors. The other Cox model is for the case in biostats in particular, where you might be taking something like blood pressure several times on a patient, and you want to be able to have what they call time-dependent covariates. So it's a more complicated model. But what we've got here is we have some fixed predictors. Those predictors are going to be the design, who manufactured the HVAC system. Was it this manufacturer or that manufacturer of a particular part in it, actually, who was the supplier, so to speak, of a particular part, A or B. These systems have fluid going through them, what the fluid velocity is, what the heat flux is, et cetera. So we're going to look at these potential X's. They're all what we call fixed predictors. They don't change over time. So we're looking at a specific fluid velocity, a specific temperature, a specific manufacturer of one of the parts, etc. We'll fill in the form. So failure time. This time we don't have to put the yes into double quotes because now we have newer dialog boxes or forms in Minitab that give us drop downs for that. My continuous predictors are all the numbers, all the ones that are numeric on a continuum. And then I have the new versus the old design and who the manufacturer was. This should look very familiar to you because it's just like all the regression dialog boxes in Minitab where we've got a model, you can add interactions, you can do whatever. We have various options. I am going to go into stepwise just to have Minitab automatically pick my model for me. So I choose stepwise, I get my model, and it turns out it comes out with an ANOVA table just like you're all used to with p-values, just like you're all used to, just like an ANOVA or regression. The two things that ended up being important in that list were the fluid velocity and the design. They did not have a significant interaction, but that's something else I could have looked at. For those of you familiar with regression in an ANOVA model, you can look at that. But these are significant, meaning their p-values were less than 0.05. Minitab automatically found this using stepwise, that it's not only the new versus the old that's important, and that is what's important to us, right? That the new design is better. But the fluid velocity, how fast the fluid runs through this, also had a significant impact on the lifetime of these heat exchangers in our test environment. Now, that equation you saw earlier is kind of the traditional Cox-Recurrent equation. What we did in Minitab was we actually took the log of both sides and changed things into just a risk score. So we saw that kind of messy equation earlier. We made it a little simpler for you in our output by taking out just the regression part and putting all the rest into something we're calling a risk score, right? So the high risk is bad, low risk is good. What we see is if we have the same fluid velocity, if we keep that constant, right, the risk for the old unit is going to be higher because we're adding 1.26 over basically the new design as our baseline risk. So, but that's what it is. It's just going to be an equation. Now, instead of y being something like a failure time, it's really our risks, because this is what we call a relative risk model. And because it's a relative risk, here's where I look at how much more successful my new design is. If I compare just the old design to the new design, and I'm using this model, so I am taking into account that important fluid velocity as well, using the model, the relative risk of 3.5 means at any given moment in time, the risk of failure for the old design is 3.5 times higher than the risk of failure for the new design. So we have had a successful new design. At any given moment in time, the old design, the unit that's out in the field, has 3 times the chance of failure of the new design, right? And we can put a confidence interval around that. Importantly, that confidence interval doesn't include 1. If the relative risk was just 1, it means old design to new design, there's no real change, right? Think of it as a ratio, 1 relative to the other. If that relative risk is 1, it just means old design and new design are the same. If the relative risk is less than 1, it means the old design was actually better than the new design, which is not the case here. Here, the relative risk is higher than 1. 3.5 times the risk for that old design over our new design. So this has been a really successful project. We can actually see this in a graph. This is very similar to the survival graph you saw earlier, except now we're using the model that includes fluid velocity. And so we can look at the reliability. So again, this is kind of a nice graph of what that model's doing, right? It's looking at not just any one point in time, it's looking at the overall hazard, or in this case, we're displaying that as just the overall survival, taking into account all these different predictors. And we see much better survival for the new design. Okay, so we are kind of getting to the end. This is just a summary of the things you've looked at. I know there are a lot of questions out there that we probably won't have time for all of them, but we can answer them offline as well. So I'm going to actually send this back to Sean for a minute because there's a few things that he needed to discuss, and then.
Yes, thank you so much, Cheryl. We hope everyone enjoyed the presentation today. We ask that you please submit any questions you'd like answered today or via email after this webinar in the Q&A box now. We also ask that you provide your valuable feedback by taking the survey accessible from the pink survey box at the bottom of this window. Cheryl, before we go into talking about the exchange event, I wanted to go through some of the questions that we've gotten. So the first one here that I want to touch on is, can you compare one design to another in reliability and determine if the difference is statistically significant?
Yes. So we did it one way, which was by taking into account other variables. You know, in this case, it was fluid velocity as well as the manufacturer of a specific part, et cetera. And we did that using Cox regression. If instead you only have just one factor, so to speak, that you want to compare, you can do that directly in the parametric and non-parametric distribution analysis dialog boxes. They both have tests for differences when you use a bivariable. So yes, that is possible.
Can you touch on what to do if the censored data does not adequately fit any of the known distributions?
Yeah, what I would do is non-parametric. Sorry, I'm scrolling, trying to find a slide and it doesn't move very fast. But that's the advantage of non-parametric. So we covered both parametric and non-parametric, but non-parametric has no distribution assumptions. And that's the other power of Cox proportional hazards. You know, I mentioned it's semi-parametric, but really the failure time distribution is non-parametric. It's not assuming a Weibull or anything else. So it works really well for that.
Got it. Let's see here. Is there a minimum number of data points needed for Weibull analysis to be considered valid?
Valid will depend on your scenario. There are some kind of power and sample size calculations you can do in Minitab. It actually depends. Are you just trying to estimate like the 5th percentile? Then you don't necessarily care when the other 95% fails. So you need a smaller sample. In terms of when you can get estimates, this is kind of crazy, but it turns out you really only need one failure, so to speak, if you know the slope of the line on the probability plot. With 2 failures, you can get an estimate without even knowing the slope of the line, right? Because all it takes is 2 points to estimate a line. So if you think about where these estimates come from, if you're assuming a distribution, it's really a probability plot. It's the best fit line through your failure times that are the blue dots on a probability plot, right? Only takes 2 points to create a line, and it turns out if you know the slope of the line, you don't even need 2 points. You just need 1. Is that enough? Sometimes it's the best we have, especially with highly reliable parts out in the field. So that's where what we do in that case is we really focus on the confidence interval and specifically a lower bound, right? So with a point or 2, we can be 95% confident that, say, our 5th percentile will be at least this amount of time. And that's usually what we do in the very, very small sample case. But again, we're also taking into account all the units out in the field. So even though you only have, say, 2 failures, you might have hundreds out in the field.
Another question here. How different would it be to use these methods for dimensional data sets rather than time sets?
You can do the same thing. So if you're looking at the common dimension that we look at in reliability is strength, right? All the time we do tensile strength and stuff using reliability analysis. Tensile strength also tends to follow either an extreme value distribution or a Weibull distribution. So yeah, these are commonly done for other types of metrics.
Great. I think we have time for 2 more questions. One here is, does the reliability module come standard with Minitab? If so, how do I find it? If not, how can I get it?
Yeah, so the reliability techniques themselves are in Minitab stat reliability survival menu. What they don't have is the module has all the guidance as to when to use which technique. The module is an add-on, and you can go to minitab.com and you can get it there, I believe. But it is an additional cost add-on. Hate to say that. I don't work in sales, so it's hard for me to answer questions like that. But yes, you can get it through minitab.com.
Okay, great. And then last question here to wrap up the Q&A. And thank you, everyone, for asking your questions. We'll do our best to get back to you via email. But the last one here is, can a Weibull analysis be combined with process control in a production setting? SPC, Education Hub, and SPM. We also also offer training, statistical consulting, and technical support services. I want to thank you all for attending our webinar today. I want to give a special thank you to Cheryl for presenting our webinar today and doing a great job and